This lecture is Climate Change Part 3. So far, we've discussed the overwhelming scientific evidence that our climate is changing. It is because of humans, and it is because humans mainly are burning fossil fuels. Now, as fossil fuels burn, gases get into the atmosphere. And we've already talked about how these gases, these greenhouse gases, trap heat reflecting off the surface of the Earth from the sun, and that in that way warm the Earth. So these greenhouse gases warm the Earth. And we said that this is a normal and natural event. However, humans, by burning fossil fuels and through other processes, have put more of these greenhouse gases into the atmosphere. So are all of these greenhouse gases equivalent at their ability to heat the Earth or to trap the gas? Well, on the left is listed some greenhouse gases. And if we said carbon dioxide, if we set that at a relative heat trapping ability of 1, so as the lowest heat trapping ability gas, then if we looked at methane, which is another greenhouse gas, we can see that it is 25 times as powerful as carbon dioxide at trapping heat. Now on the right-hand column, we can see the lifetime in years of these greenhouse gases in the atmosphere. Carbon dioxide is variable, but methane stays in the atmosphere for 12.2 years. Nitrous oxide, which is produced from car exhaust and power plants, is 298 times as powerful as carbon dioxide at trapping trapping heat, and it stays in our atmosphere for 120 years. Now, carbon dioxide, methane, and nitrous oxide are naturally found in the atmosphere, but we have increased their concentrations through the burning of fossil fuel. The next gas listed here is hydrochlorofluorocarbon, or CFCs. And you can notice here that these are much, much more powerful than carbon dioxide. In fact, 14,800 times as powerful as carbon dioxide at trapping heat within our atmosphere. And unfortunately, they stay in our atmosphere for an awful long time. CFCs are not naturally occurring, and we added these. And we had talked a little bit about how that was in the past. Luckily, based on the Montreal Protocol, most of the developed nations of the world had stopped producing CFCs, and so the concentration is starting to go down, but it is expected to take a long time. When we look at these gases, especially carbon dioxide, some people ask, well, how can you tell what proportion of carbon dioxide in the atmosphere is from humans and what part is naturally occurring? Well, believe it or not, we can differentiate natural CO2 from man-made CO2 by looking at isotopes. Isotopes are heavier forms of an element and allow us to distinguish which CO2 is man-made. So again, in looking at this table, which greenhouse gas has the least ability to trap heat? If you guess carbon dioxide, you would be right. Which has the greatest ability to trap heat? Well, CFCs. Which greenhouse gas is the longest lived in our environment or in our atmosphere? Again, that would be CFCs. So if carbon dioxide has the least heat trapping ability, why are we worried about it? Well, in this graph, you can see on the x-axis is the years, and so they start around 1000 and they go up to about 2017. And then we have two y-axes. So the y-axis on the left is methane levels in parts per billion. A part per billion is equivalent to, think of putting 1 drop of ink in the largest tanker truck used to haul gasoline. So 1 drop of ink in the largest tanker truck you can imagine hauling gasoline, that's 1 part per billion. On the right side y-axis, it's also parts per billion for the nitrogen oxide gases. But for carbon dioxide, it's parts per million. So a part per million is 1,000 times greater than 1 part per billion. Whereas a part per billion would be 1 drop of ink in the largest tanker truck you can think of. 1 part per billion would be like 4 drops of ink in a 55-gallon drum. So when we look at this graph, you can see that clearly carbon dioxide is in much higher concentrations than any of the other greenhouse gases. And when you look at it, don't just think it's this much higher, because remember that the CO2 levels are measured in parts per million. So if we were to draw this to scale with the same units on the y-axis, the methane and the nitrous oxide levels would be way down here. They wouldn't even be anywhere near carbon dioxide. So carbon dioxide is clearly the most abundant greenhouse gas, even though it's not the most potent. And it is the major contributor to global warming. So human activities have boosted the atmosphere concentrations from about 280 to now we are greater than 410 parts per million. And this is the highest level of CO2 we have seen in about 800,000 years. But more likely, it is the highest level in the last 20 million years. So what's causing the levels of CO2 to increase? Well, the main thing is burning of fossil fuels. And this is through homes, factories, and cars. The other way we are releasing CO2 is through deforestation, the cutting down of trees, because remember that trees and forests serve as a sink for carbon. Trees and plants need carbon dioxide, and so it's stored in their tissues. This is a graphic that was put out by the Carbon Project that looks at what's called a carbon budget. And you can see on the left, they're showing you the sources, the major sources of carbon dioxide. And the units are gigatons of carbon dioxide per year. A gigaton is 1 million tons. So you can see that 87% of all CO2 coming from man, anthropogenic means from man, not naturally occurring, is coming from the burning of fossil fuels. 13% is coming from deforestation. On the right-hand side, they're showing you the sinks. Where is the carbon stored? And you can see that most of it is in our atmosphere, where it's having a warming effect. 29% is stored in our forests, but certainly as we cut those down, it's released to the atmosphere. And then 22% in the ocean. When we look to warming, there are some things that lead to warming, and those things in this picture are showed above the zero. And there are some things would actually lead to cooling, and those things are shown below the zero. So clearly you can see the major contributor to warming is carbon dioxide. And the second major contributor is actually other greenhouse gases, including ozone. Now ozone, keep in mind, when it's in the troposphere, which is the part of the atmosphere that we live in, so from the surface up to maybe about 7 miles, it causes a warming effect. But when ozone is in the stratosphere, which is above the troposphere, it causes a cooling effect. If we look at surface albedo, now we're going to talk about albedo in a minute, but just so that we're all on the same page, albedo is the ability to reflect the sun's energy back to space. So the ability to reflect the sun's energy back to space. So surface albedo means the ability of the surface, which would mean mainly snow. So things that are clear and white, like snow and ice, are very good at reflecting sun's energy back, and that cools the Earth. But if there's any soot on the snow, that is actually going to warm, because then the snow isn't white, and the black in the snow absorbs heat. Aerosols in the atmosphere cool, as does cloud albedo. So that's the ability of clouds to reflect the sun's energy back. Before we move on to focus solely on carbon dioxide, let's look at some of the sources of other greenhouse gases. So in this picture, we can see methane. Now, methane is a very potent greenhouse gas. It is much more powerful than CO2, and the levels of methane have increased 2.5-fold since pre-industrial times, which would be in the 1750s. So you can see the sources here. One source, of course, is fossil fuels, the burning of fossil fuels. Another source here is landfills, which release a lot of methane as material is deteriorated by bacteria. And then we have livestock, and it's actually through the release of gas of livestock that methane is produced, and it's significant. Another greenhouse gas is nitrous oxide, you can see down here, and this has increased 20% since the 1950s. So one major source is fertilizer. Another is the chemical industry. And a third would be feedlots. Feedlots are giant acres and acres where animals are raised for meat. Some other greenhouse gases include ozone in the troposphere, remember, which is formed mainly by chemical reactions between chemicals that are released by cars. The major source of ozone is industrial facilities, chemical facilities, and cars. CFCs, remember, probably the most potent greenhouse gas. Well, the CFC levels are already decreasing due to the Montreal Protocol. And we've already talked about some of the sources of CFCs, but remember, they were used as refrigerants. They were used in sprays in different household products, like, for example, deodorant. But these uses have all been phased out. Lastly, we have water vapor, which is very abundant, and the concentrations of water vapor have not really changed over time, at least not significantly. But the thing with water vapor is that its major way of getting in the atmosphere is evaporation of water. So as the temperature increases, you would expect to get more water vapor in the atmosphere. And that water vapor would cause more warming, which would cause more evaporation. So this is kind of, you can think of it as a positive feedback loop, because the change just keeps going in the same direction. So now let's focus a little bit on carbon dioxide, which is the major greenhouse gas. If we look at this graph, which was produced by the Carbon Project, you can see on the y-axis is amounts of CO2 in gigatons. So this is annual emissions. And on the x-axis, you can see years. And then we have these different countries which are color-coded. Which country is the major contributor of greenhouse gas currently? Well, it's obviously China. In fact, China's just in 2017 increased its emission of CO2 by 9.8, or by 1.7%. The U.S. is number 2, but our emissions have gone down 0.5%. EU, the European Union, is number 3. Their emissions went up 1.4%, and then India would be the last, and their emissions went up. So these top 4 emitters are covering about 58% of global emissions. So China's number 1, the United States is 2, European Union is 10, and India is 7. So who should lead the reductions of carbon dioxide? Who should do that? Well, here's another graph that shows you kind of the same thing. The data's a little older here, but you can see even in 2013, China was still the number 1 emitter. US was number 2, European Union number 3, India number 4. So that's the same. But on this side of the graph, we can see per capita emissions. Per capita means per person. So per person, which country per person is releasing the most greenhouse gases? Well, we can see the United Arab Emirates here, Australia, Saudi Arabia, Canada, and of course the US. China is not number one, neither is India. So this means if you look at people's individual contributions, the countries that are more developed and more wealthy are releasing more CO2 per person. This is a graph of the cumulative emissions of different countries' release of CO2 over the years, and it starts in the 1850s. So let's watch how this changes over time. Okay, so now we're in 1850, and you can see this is England, US is number 2, this is Germany, now Germany's, now the US, this is France, back down here, the Netherlands, Canada, and now Japan is on the scene, this is India, and now, you can see the US is outpassed by quite a bit. England, 1897, Germany starting to rise up, the US is still well above the other countries, so we have Germany, England, France, this is Canada, Japan, India, now we have China is on the scene. China, and this is the Netherlands, by the way, right here. Germany, US is still pretty high up there. And now we can see India right here. China and France, Germany. So now we're into the late 50s, 1960s. The US is still high above everyone else in terms of greenhouse gas emissions, but we can see China is starting to move up. China's the red with the little yellow star. Now we're into 1980s, 1990s, China's moving above, and now we can see China really starting to rise in the 2000s. And now they've beat out the US as the number one emitter, 2010, 2011. And you can see India is right behind the US. Given what we just saw here, does this change your mind about who should lead the reduction? One question is, who has put most of the man-made carbon dioxide in the U.S., at least according to this? And this is cumulative over 100 years. And the answer is clearly the U.S. has done that. Who is the major emitter now? Well, it's China. But it wasn't always China. So if you take a look at China here they are, right here, you can see that they really didn't start contributing until the late 1980s. Their contribution was very low to the carbon dioxide that's currently in the atmosphere. So again, the question I have for you is, who should lead this reduction? This is just a figure that shows you the emissions per state, at least in 2015, and you can see that Texas, California, and Pennsylvania led the amount of greenhouse gas emitted. Massachusetts is fairly low, and then we have some other states like Rhode Island, Vermont at the very end. Now, one thing to keep in mind is that even though the federal government currently is really taking apart legislation to help prevent climate change, individual states are still pledging to have zero emissions of greenhouse gases in a very short period of time, and that includes the state of California, and also Massachusetts, Vermont, New Hampshire, Maine. There are just a tremendous amount of states now that are going forward despite the federal government's lack of action and making pledges and planning how they're going to cut their carbon emissions. Okay, so again, we know our climate is changing, is warming. We know that the major greenhouse gas is carbon dioxide, and we put it there. What are the impacts that are occurring, most of which are actually occurring now? Well, they're kind of what you would think they would be. An increased temperature on land and ocean. Changes in precipitation. So more rain in some regions, less rain in others. Melting ice, that's sea ice and glaciers. A rise in sea level. The sea level has risen about 7 inches over the last 100 years. Ocean acidification. Weather extremes. Droughts are longer and more extreme. higher frequencies of extreme weather events like hurricanes, tornadoes, and fires, and then impacts on species, including humans. So let's look at these impacts more closely. I'm going to start with temperature. So according to the IPCC, the increase in average world temperature by 1.5 to 4.5 degrees centigrade by 2100. That's what they expect. But there's been newer data now that shows that this lower end of the range is unlikely. In other words, the changes they are expecting now are going to be at the higher end of this range and unlikely to be below 2 degrees centigrade. Now, why this is a big deal is remember that Earth's temperature, average temperature, has only changed by 4 to 7 degrees centigrade since the Ice Age. And the Ice Age was a very different time on Earth, a very different climate. And now we're talking about the same magnitude of change. Increased heat waves are expected, defined as 3 or more days above 90 degrees Fahrenheit. In Massachusetts, the temperature is expected to increase from 2.9 to 5.3 degrees Celsius, with greater increases in the winter of temperature. Precipitation is expected to increase in Massachusetts. Increased length and severity of pollen season. Increase of vector-borne diseases such as Lyme disease, Zika virus, Eastern equine encephalitis, Nile disease, West Nile disease, and a decrease in cold water species, for example, lobster and cod. Now, when we look at this overall temperature change, we are committed to 50% of this warming. So no matter what we do, we are going to see at least 50% of the warming predicted here, due to a slow response of our climate to changes in greenhouse gases. So in other words, if we stopped releasing greenhouse gases today, that change would not take place in the atmosphere for another 30 years. There is a lag time. So the atmosphere is very slow, the climate is slow at responding to those changes. By 2100, IPCC predicts that the average global temperature will increase by about 3.2 to 7.2 degrees Fahrenheit over today's temperature. So I put this in here just because most people are more familiar with Fahrenheit than they are with Celsius. But this is what the IPCC is predicting. However, the rest of the change is strongly influenced by today's emissions. So let's take a look at the globe here, and you'll notice there's a little legend over here. And this shows you the percent increase in temperature in degrees Celsius. So the lighter colors mean there is less of a temperature increase. But as you go from yellow to orange to dark orange to red to maroon, the temperature increases more. My question is, where is the temperature going to increase the fastest? Well, you might notice that most of the change, most of the red is up here in the Arctic. And that's where the climate is expected to increase the fastest. Another impact is heat waves will increase, especially for cities. And that's because of something called the urban heat island. The urban heat island is that when the temperature is high, buildings and pavements absorb that heat during the day, but then at night they slowly release it. So the temperature stays high at night, whereas in the country it would be lower. So if we take a look here, you can see this is one model in the heat index, and it's showing you the increase in temperature that's expected in July. And you can see that here in the southeast, it's going to be incredibly high. We're talking about plus 25 degrees Fahrenheit. In Massachusetts, it looks like we're somewhere between plus 10 and maybe plus 15 to 18, something like that. This is showing you some of the major cities and the deaths per 100,000 people due to heat waves. Now again, this really affects the elderly more than others, and it also affects people who do not have access to air conditioners. So you'll notice 1964 to 1991 is the orange in the city. This is how many deaths there were per 100,000 due to heat waves. In 2020, the projection really jumps, not so much for Atlanta, but Chicago, Minneapolis, New York. These are areas that are in the north. And then in 2050, it's even higher. By 2050, scientists predict that heat-related deaths in Boston could be close to 150 deaths per summer. That's a 50% increase over the current rate. This is some data from 2015 where there were extreme heat in some of these areas. And what I'd like you to notice is the number of people who died and where that happened. So, you know, if you look, you'll notice India, Pakistan, and then the others don't even really mention people dying. I mean, in Japan, there were people admitted to the hospital, but these are the countries that are least able to adapt to these changes, where there is a lot of poverty. People do not have air conditioning, and so they're much more susceptible to the change in climate. What other impacts do we expect? Well, melting glaciers. Glaciers are disappearing on tropical mountaintops. Glacier National Park is known, it's named for its glaciers. Only 25 of the 150 glaciers currently remain, and they're expected to be all gone within a couple of years. The other impact of melting glaciers is that in the summer, when the glacier normally melts a little bit, it provides water for the people that rely on the mountain meltwater. And once the glaciers melt, there will no longer be this water supply for them. And this is already happening in the western part of our country. This is a picture from Glacier National Park, which is in Montana. And this is the Grinnell Glacier, which is the most visited glacier in this park. And you can see in 1938, it was huge. This is the glacier. It's a little hard to see, but this is all the glacier. This is 1981, and you can see where the glacier has melted, 1998, 2006. So the glacier lost about 45% of its footprint. The ice in this glacier used to be 20 to 30 feet high. Now, if you go to visit it, it only comes up to your shins. These are other glaciers in Glacier National Park, and you can see the gray areas was where they used to be, the blue areas where they were in 2015, and you can see they have lost tremendous amount of the sea ice, of the glacier. This is the Muir Glacier in southeastern Alaska, and you can see here very well in this picture was huge, and now look at it in 2004. This glacier retreated more than 7 miles, permanently retreated. So that's glaciers. And again, the downside is that when you lose those glaciers, the heat is no longer reflected back into space, but instead is absorbed and heats the planet more. But the other part about losing the glaciers is there's no longer a drinking water supply in the summer for people who live in the valleys. So this melting of ice and this reflection is called surface albedo. Surface albedo means the capacity to reflect light. When you have ice or snow, which is white, it reflects the light back into space and it cools the temperature. But when the ice melts and you have a darker surface, the sun's energy is absorbed, which heats up either the water or the land, which causes more melting. And so this becomes a positive feedback effect. Now, sea ice is also melting. The Arctic sea ice has dropped by 40% since 1960. If we take a look at the graph, you can see on the x-axis is years, and on the y-axis is percent change in ice cover. The black dots on here are actual satellite observations, so they're real data. And then the orange line in the middle is what the IPCC predicted for the future in terms of loss of ice. So you can see you're at 0, so once you go below 0, you're losing ice. But then, actually, a couple of years ago, they actually went out and measured the sea ice, which is what the white line is. And they found that the sea ice was melting 80 years early ahead of schedule. So it was melting much, much faster than they had predicted. And most of the models are very conservative, meaning they looked more towards a worst case. This is actually a video from NASA showing the sea ice shrinking over time over the Arctic. So let's take a look at this for a minute.
Satellite observations by NASA show sea ice coverage in the Arctic has reached an annual low. The sea ice receded to an area of 1.94 million square miles on September 17, 2014, making it the 6th lowest extent on record.
Arctic sea ice basically acts as a big air conditioner for the planet. When the sun shines down on it, most of the energy is reflected away. So it helps to keep the planet cool. Since 1979, we've been monitoring the extent of sea ice with satellites. And at the present time, we've lost an area equivalent about a third of the United States. It goes up and down every year, but the long-term trend is that we've been losing a lot of sea ice. In large part, what's been causing the decrease has been heat. The Arctic has been warming up, especially in the last 10 years. The temperatures in the Arctic have risen about 2 to 3 times the global average. So increases in the global temperature have been decreasing the thickness and extent of Arctic sea ice.
The total volume of sea ice at the end of the summer melt season in 2013 is about 2/3 less compared to 1979.
The loss of Arctic sea ice thickness, it makes it less resilient. If it's just not as thick, what happens is that it melts faster, and because of this, it just doesn't stay around as long in the summer. It's important that we're looking at Arctic sea ice because of the large impact that it has on our climate. It's basically one of the most significant symbols of a changing planet.
Okay, so a couple of things you might have heard. One is that the Arctic sea ice acts as an air conditioner for the planet by reflecting heat. Another is that we lost an area about a third the size of the U.S. in terms of sea ice. And lastly, the Arctic is warming a lot faster than the rest of the planet, 2 to 3 times faster than the global average. This article came out in 2014, and it showed that the Antarctic is also melting and is unstable. So this was an area of the Antarctic called the Amundsen Sea section, and in this area there are 6 glaciers on land, and they sit on bedrock. However, they're unstable because the melting is occurring underneath them. So between the bedrock and the glacier is a layer of water as the ice melts. And what that does is it makes it easier for the glacier to slide into the ocean. That would be catastrophic, because if it did slide into the ocean, it would raise the sea level about 3 feet worldwide. And this would displace millions of people, just from the glacier melting, not from anything else related to climate change. They are predicting that this will happen in the next 100 years. Another problem with melting sea ice is that as it melts, pathways open up for people to explore this area around the Arctic. And what nations are rushing to this area now to see if they can find underwater oil and mineral resources. And nations are positioning themselves to stake claims over this part of the ocean. So of course this is a problem, because if people are taking out more fossil fuels to burn, it's just going to accelerate the warming of the planet. Another impact of melting sea ice is the melting of something called permafrost. Permafrost is permanently frozen ground. And what happens is under the ground there is a layer of ice. It's a little hard to see here, but there's a layer of ice in the earth, and it's been that way for a long time. But now it's starting to melt, especially in the Arctic. As it does, it destabilizes the soil and buildings. So if buildings are on it, the buildings can bend or can tilt or can collapse because the soil underneath is no longer stable. On top of that, the melting ice releases methane, which has been trapped there for thousands of years, which further warms the planet, causing the more melting of permafrost. Here are some examples of where the permafrost is melted. In this picture here, you can see the layer of ice, which is under the soil. In this picture, you can see a whole part of the coastline just fell off, and you can see the ice right here. This picture is from Siberia, where a 200-foot wide crater was discovered, and as of now, they're calling it bottomless because they can't find the bottom. Here is in the Arctic, and you can see what happens is very typical when permafrost melts, is that the land underneath caves in, and so these trees that have roots in the soil start to tilt and kind of wobble. This next little video is of a professor in Alaska, and they're showing you how methane, not only is it trapped in the soil, but it's trapped in the sediments of lakes.
We're out standing on a frozen lake in interior Alaska, outside of the University of Alaska Fairbanks campus, and this ice is already about 20 centimeters thick, so as it's been freezing up, methane gas has been coming out of the bottom of the lake and getting trapped in the lake ice. If you look at the shore, you can see that there are lots of trees that are falling in the lake and they're dying. What's happening is the permafrost is thawing. The ice that was in the ground, when it melts, causes the ground surface to collapse. So the forest falls in, and any organic matter, dead plant and animal remains that were in the permafrost, thaw out in the bottom of the lake. Microbes decompose it, and it generates methane. And methane doesn't like to stay in water in solution. It forms bubbles, and those bubbles make their way to the surface. In the summertime, the bubbles pop and they enter the atmosphere. In the winter, however, this ice forms a cover on the surface of the lake, and the bubbles get trapped right under the ice, and the ice thickens and freezes around them. So what we have out here is like a time-lapse photograph of methane emissions from the lakes. Methane is a very potent greenhouse gas. A molecule of methane is 25 times stronger than carbon dioxide. Methane is formed in millions of lakes around the Arctic where permafrost is thawing. And each year, these lakes are emitting already tremendous amounts of methane. But when we look at how much carbon is in permafrost still frozen, and the potential for that permafrost to thaw in the future, we estimate that more than 10 times the amount of methane that's right now in the atmosphere will come out of these lakes.
Okay, so again, a big problem of melting permafrost is the release of methane. Other impacts of the warming of our climate is rising sea levels. So rising sea levels are partly due to the runoff from melting glaciers and ice as it enters the ocean. And this causes sea level rise. But the major reason for the sea level rising is because as water warms, it expands. And so that's what's happening. You can see here the sea level rise over years. So 1.8 millimeter a year, which is probably about 0.007 inches. And then we have 2.9 to 3.4 millimeters a year, which is 0.11 inches. But by 2100, we're looking at a change of 7 inches to 4.3 feet, a tremendous increase. Now, even small rises in sea level can lead to beach erosion, also coastal flooding, intrusion of salt water into aquifers, and greater impact from something called storm surge. Storm surge is a temporary rise in sea level from high tides and storms, where the water comes up much further on the shoreline. Storm surge can have tremendously damaging effects on communities, and we can see some examples here. This example is the Maldives. The Maldives are a group of about 1,200 islands, and they are south of Africa. And about four-fifths of the land is only 39 inches above sea level. So they are incredibly susceptible to rising sea levels. What happened in 2004 was that there was an earthquake, and the earthquake caused a tsunami, which produced a tidal wave. And this tidal wave killed 100 Maldive people. It cost about $470 million in damage. If we look over here, this is Hurricane Katrina, which was in 2005, and this killed about 1,833 people. It caused $50 billion in damage. And it was due to a rising sea level, a warming ocean that had more energy, so produced a more powerful hurricane, and also they had lost a lot of their coastal wetlands, which could have protected them a little bit from the hurricane. Down here is Hurricane Sandy, which happened in 2012. 130 people were killed. It cost about $60 billion in damage and left thousands of people homeless on the East Coast. And these are all more severe because of climate change. Now, more recently, we had Hurricanes Harvey, Irma, Jose, and Maria that caused $200 billion worth of damage in Texas and also in Puerto Rico. The death toll in Puerto Rico was 2,975 people. And this was either direct or indirectly from the hurricane. So rising sea levels can be incredibly devastating, and probably more so for countries and people who are not prepared and who are living in poverty and don't have a lot of resources. Well, who is at risk from storms in the U.S.? Well, 53% of people live in coastal areas in the U.S. And you can see here the sea level trends, where the sea level rises are expected. Some of the areas are darker, meaning they're expecting to get a higher sea level. And of course, New Orleans here has already been devastated with that. Even in Massachusetts, sea level rise has been calculated, and this is a scenario they're expecting in the year 2100. So here's Boston. Everything in this light blue is expected to be underwater. And so cities, major cities like Boston and New Orleans and New York are already planning for this. In fact, most of the world's population is on the coast. If you look at this table on the left, these are the top nations which have the most people living in low-lying areas. So you can see China is number one with, well, no, China's not number one. China has the greatest population. So if we look at the total number of people, they would have the most people living near the coast. But the greatest percentage of people of a country would be Bangladesh and Vietnam. And of course, these countries, China, India, Bangladesh, Indonesia, Vietnam, are the least able to adapt to changes like this. This table on the right is looking at nations classified by the proportion of their population living in low-lying areas. So in the Maldives, everybody who lives there is in a low-lying area susceptible to climate change. Bahamas, Bahrain, Suriname, so these are places where everybody, the Netherlands, are in areas that will be affected by rising sea levels. So when we think about this, we have to think a little bit about the concept of environmental justice. Environmental justice means fair treatment and involvement of all people when developing and implementing environmental regulations. So it's fair treatment and involvement of all people when developing and implementing environmental regulations. It's also the fair treatment of all people when developing sustainable solutions to environmental problems. So in this picture, we have two countries, the Netherlands, who have a tremendous amount of people who are at sea level and susceptible, and India, who's the same. And the difference here is that the Netherlands are much better able to adapt to rising sea levels. In fact, they're already doing it. You can see here, these are homes that are built on these platforms on the water so that when the sea level rises, the homes rise with them. And there are many other adaptations the Netherlands has already developed to prepare themselves to survive climate change. But in poor countries like India with massive amounts of people, they don't have those resources and they haven't made those adaptations. And so the impacts of climate change are going to be heavier on people who are less able to adapt to it. If you remember from the earlier graph, the Netherlands was a major contributor to the CO2 that's already in the atmosphere. So the impacts that we're feeling today are because of nations like the Netherlands and the US, but the people who are experiencing them or the least able to adapt are countries who did not put the carbon dioxide there. If you take a look at the websites listed here, they talk about other countries who are being impacted, and one in particular is Africa. It's a great little video to watch to see how they're already being impacted and how they're dealing with it. This is a slide that just goes back to sea level rise, which shows you that there are many causes for sea level rise related to climate change, but the biggest contribution is thermal expansion. So that means the expansion of water when it warms, which causes the sea level to rise. Other impacts of warming of oceans, well, it's a big risk to coral reefs. Most organisms within coral reefs survive within a very narrow temperature and pH range. So they're not able to adapt. Also, the collapse of the Gulf Stream is a possibility because as you remember, as more fresh water enters the salt water, it dilutes it, making it less dense, and that can actually slow down the currents within the world. In fact, most warming due to climate change has been in the oceans, as you can see in this picture right here. The more heat, that is, the more warmer the ocean is, the more energy it has, the stronger storms can be developed. Remember that the 2014 IPCC report predicted an increase of about 1.5 to 4.5 degrees Celsius by 2100. And here we're seeing that 40 to 70% of species at risk of extinction with just a 3.5 degrees Celsius warming. So we're already seeing this. We're seeing coral bleaching, which is when coral dies. We're seeing cold water species like the cod moving out of places and heading north to colder areas. And we're also seeing plants no longer being able to stay in the areas that they were formerly because it's too warm. Another impact on the ocean is that they are acidifying. So a common reaction that happens in nature is when you have carbon dioxide with water, it often forms this compound called carbonic acid. Now, carbonic acid is not very stable, and that will quickly break into hydrogen ion plus a bicarbonate ion. And this hydrogen ion is what causes acidity. So normally what happens is in oceans there are a lot of salts, and so the salts will buffer the acidity. That means the salts will take the hydrogen ion out of solution so the water won't become acidic, and then the sea organisms use the carbonate plus calcium to make calcium carbonate, and this is used to make shells. And so that's what the oceans have been doing for a long time. They've been taking the carbon dioxide, which is absorbed in the ocean, and using the bicarbonate to make their shells. And the salts in the ocean have buffered the acidity. But we've reached a tipping point where the salts in the ocean can no longer buffer, can no longer bind up the hydrogen ion because there's too much of it, because there's too much carbon dioxide. So if we look at this graph, you'll see the year on the x-axis, and there are two y-axes. One is the concentration of carbon dioxide in the atmosphere, and the other is the pH. Now remember, the pH is a measure of the hydrogen ion concentration. And if the more hydrogen ions you have, the more acidic. So based on that, what can you conclude from this graph? What does this graph tell you? Well, one thing it tells you is that the pH is going down. That means the oceans are becoming more acidic. The second thing you can see is the CO2 level in the atmosphere is going up. And the last thing you might notice is the two seem to be correlated. That is, pH and the CO2 levels are related. As the CO2 level goes up, the pH level goes down. And this is exactly what's happening. Now, why is it a problem? Well, as we said, carbon dioxide in the atmosphere turns into hydrogen ions in the ocean, and that is corrosive to the shells and skeletons of many marine organisms. Corals can survive only within a very narrow pH range. Plankton in the ocean are made of calcium carbonate shells, which will be dissolved by the hydrogen ions. Remember that these plankton are the basis of the food chain in the ocean. And the other thing they do is they produce about 50% of the oxygen in the atmosphere. So they are very important. Even lobsters are not growing as large because of the acidity of the ocean. A low pH destroys coral reefs. At 370 parts per million of CO2, we expect an increase of about 1 degree centigrade. At 450 to 500, 2 degrees centigrade, and the acidity goes up. And here is what you would expect to see. And you notice there's a lot less organisms, there's no algae here, and then here's what you see at about 500 parts per million, which is nothing.